Imagine a magnetar appearing halfway to the moon. Its magnetic field would instantly wipe every credit card on Earth. Love mind-blowing space facts? Subscribe. In 2004, a magnetar unleashed a rapid flare, packing more energy in a split second than our sun creates in 100,000 years, disrupting our atmosphere from 50,000 light-years away. Contrast this violence with absolute silence. The universe is 14 billion years old, yet red dwarf stars live for 1 trillion years, meaning not a single one has ever died. From immortal survivors to physics-crushing monsters, we are exploring 18 extreme star stages. Stick around. Recent James Webb discoveries could rewrite everything we know about their deaths.
But before a star can die, it has to be born. And sometimes the universe just fails. Enter the brown dwarf, the ultimate cosmic reject. Straddling the line between the heaviest planets and the lightest stars, they pack 13 to 80 times the mass of Jupiter. They can briefly fuse heavier isotopes like lithium, but completely lack the pressure needed to ignite regular hydrogen fusion. They just slowly fade out. Picture a dark world sitting around 4,000 degrees Fahrenheit, where the weather forecast literally calls for violent storms of molten iron rain. If a star does manage to ignite, it usually becomes a red dwarf. These are the silent rulers of the cosmos, making up roughly 75% of all stars. Packing 8 to 50% of our sun's mass, they sip their fuel so slowly that their lifespans stretch past 1 trillion years. Since our universe is only 14 billion years old, no red dwarf has ever died. The famous TRAPPIST-1 system is a red dwarf hosting 7 Earth-sized planets, making it a prime hunting ground for alien life. But for the ultimate cosmic real estate jackpot, look at orange dwarfs. Weighing 60 to 80% of our sun, they are the sweet spot for habitability. They are far more stable than red dwarfs, throwing fewer deadly solar flares, and they burn steadily for 15 to 30 billion years. This gives potential life a massive head start. Speaking of home, our sun is a yellow dwarf. Here's a plot twist. They're not actually yellow. If you looked at our sun from deep space, it would be blindingly white. Earth's atmosphere scatters the shorter blue wavelengths, tricking your eyes. At 4.6 billion years old, our sun is right in its midlife crisis. Before we look at star death, we must mention the ghosts of stellar evolution, blue dwarfs and subdwarfs. A blue dwarf is entirely theoretical. It is what a red dwarf will eventually become when it runs out of hydrogen, burning hotter and turning blue. But the universe is simply not old enough for one to exist. Subdwarfs, meanwhile, are ancient, dim, and metal-poor relics from the early universe, hiding in the galactic halo. When stars like our sun finally exhaust their fuel, they leave behind a super-dense tombstone, known as a white dwarf. Imagine crushing the entire mass of our sun into a sphere the size of Earth. Gravity becomes so extreme that a single teaspoon of this dead star would weigh roughly 11,000 pounds. Over billions of years, the carbon core cools and crystallizes. The end result is a diamond star, a flawless, planet-sized diamond drifting silently through the endless void. But while these dwarf stars fade quietly, the true giants of the universe prefer to go out screaming.
Let's look at Earth's grim future. When stars run out of hydrogen in their cores, they start burning it in their outer shells. This causes them to swell violently. Despite their massive size, their surfaces actually cool down, giving them a menacing red-orange glow. It is a terrifying preview of our own doom. Fast forward 5 billion years, our sun will become a red giant. It will expand so aggressively that it will swallow Mercury, Venus, and most likely completely vaporize Earth. But if a red giant is a tragedy, a blue giant is a cosmic rock star. Live fast, die young, and leave a gorgeous corpse. These stars burn at staggering temperatures, easily exceeding 18,000 degrees Fahrenheit, blindingly bright and incredibly hostile. Because they consume their fuel so recklessly, they only survive for a few million years. And then there are the blue supergiants. Weighing up to 100 times our sun, they are the hottest, most luminous monsters out there, shining hundreds of thousands of times brighter. When they die, they don't just fade, they detonate in catastrophic supernovas. Yet, if we are talking pure, terrifying size, nothing beats the red supergiants. These are the morbidly obese kings of the cosmos, bloated to incomprehensible proportions as they exhaust their final energy reserves. If you dropped a famous red supergiant, like Betelgeuse, into the center of our solar system, its surface wouldn't just reach Earth, it would swallow Mars and practically touch the orbit of Jupiter. They are incredibly unstable, violently dying beasts, just waiting for the final collapse. And at the absolute peak of cosmic extravagance, we find the hypergiants. These are the brightest and most massive stars ever discovered. If you flew a commercial jet around one, it would take centuries to complete a single lap. They pour out millions of times more light than our sun. Take UY Scuti, a red hypergiant with a radius roughly 1,700 times larger than our sun. These stars are incredibly rare and so wildly unstable that they literally bleed mass into the void through terrifying stellar winds. They live extremely short, violent lives, and their inevitable deaths are some of the most destructive events in existence. But what exactly is left behind when the biggest stars tear themselves apart? That is where the laws of physics completely break down. Before the final collapse, some massive stars go completely rogue. Enter the Wolf-Rayet star. Imagine a stellar core that is violently blown off its entire outer shell of hydrogen. What is left is a naked, raging core burning helium directly at temperatures exceeding 360,000 degrees Fahrenheit. They are so ridiculously hot and unstable that they blast away their own mass through stellar winds, traveling at over 1,200 miles per second, creating beautiful but deadly nebulas. They are ticking time bombs, guaranteed to end in catastrophic supernovas or even hypernovas. When that bomb finally goes off, the core collapses. If the star was massive enough, but not quite massive enough to break space-time, it forms a neutron star. This is where reality gets incredibly hard to swallow. Imagine taking a star up to twice the mass of our sun and crushing it down to a sphere just 12 miles across. The pressure is so immense that electrons and protons are violently smashed together to form a solid ball of neutrons. A single teaspoon of this dead star matter would weigh over 13 trillion pounds. The surface gravity is 2 billion times stronger than Earth's, and these dead cores can spin hundreds of times every single second. Some neutron stars develop extreme, terrifying personalities. Pulsars, for example, emit blinding beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep across the galaxy like a cosmic lighthouse. When Jocelyn Bell Burnell first detected their perfectly timed pulses in 1967, scientists half-jokingly labeled the radio signal LGM-1, short for Little Green Men, because it looked terrifyingly artificial. Then there are the Magnetars. Remember that credit card wiping monster from the beginning of this video? A Magnetar's magnetic field is a quadrillion times stronger than Earth's. That 2004 flare from SGR 1806-20 wasn't just a brief light show. It physically warped our upper atmosphere from 50,000 light-years away. But what happens if gravity pushes even harder? Theoretical physics suggests a terrifying middle ground between a neutron star and absolute darkness, the Quark star. If the crushing pressure inside a neutron star crosses a critical threshold, the neutrons themselves literally shatter. They break down into a quantum soup of fundamental particles called quark matter. In 2002, the Chandra X-ray Observatory spotted 2 dead stars that were simply too small to be normal neutron stars, making them prime suspects for this bizarre state. If they exist, they are made of the strangest, most dangerous material in the cosmos. Finally, if the dying star is over 20 times heavier than our Sun, absolutely nothing in the universe can stop the collapse. Gravity wins the ultimate victory, tearing a literal hole in the fabric of space-time itself. Welcome to a black hole. The gravitational pull becomes so infinite that not even light moving at 186,000 miles per second can escape its grip. Cross the boundary known as the event horizon and you never return. While stellar mass black holes haunt the galaxy like silent predators, supermassive black holes weighing billions of times more than our Sun lurk at the center of nearly every galaxy, waiting in the dark. Humanity finally photographed one of these supermassive titans in 2019, proving the ultimate abyss is very, very real.
We have journeyed from red dwarfs surviving 1 trillion years to massive stars collapsing into devouring black holes. This universe is a cruel, beautiful cycle. But as Carl Sagan said, we are made of star stuff. The iron in your blood and calcium in your bones were literally forged in the blazing cores of dying stars billions of years ago. We are simply the universe observing itself. Out of these 18 evolutionary stages, which celestial monster amazed or terrified you the most? Drop a comment below. Hit like, subscribe, and ring the bell to catch our next cosmic journey.